Now, to understand data structures inside the Linux kernel, we first need to understand them individually. So, what is the Linux kernel? The Linux kernel is the most important component inside the Linux operating system, and it acts as an interface between the computer's hardware and the processes. It enables the communication between them and manages the resources between them very efficiently. So, for any operating system to be efficient, it needs a very good Linux kernel. Next, let us look at data structures. So data structures are a format used by the computer to store, maintain, and organize data. Now we have different data structures that have different ways of accessing data, and we can use this to effect because inside a Linux kernel, it has to be efficient and it has to manage all of the resources. We can use certain types of data structures to maximize the efficiency of the kernel. And if you ever want to read the Linux kernel source code, you need to master the basic data structures that are present. Now, there are different kernel components that use these data structures. There are process tables who maintain the track of all the active processes inside the system. Examples would be storage information, execution status, and the file information inside the kernel. We have the file table where every file in the system is represented inside this table. Each file table entry will have information such as the file status, whether it is read or write, the file offset, and so on. And in addition to this, the file table also has vnode and inode pointers, which point to the virtual node and the index node respectively. Now, the vnode and inode are the references inside the file storage system, and they are storage methods basically. They link the hardware and the software of the system. The vnode is an abstract term that provides the way for accessing file data without regard for the system's real architecture or the real structure. And the inode defines file access information such as file storage device, read-write processes, and so on. Now, this was not an exhaustive list of all the data structures. For example, different kernels will have different data structures, like IBM's AIX servers. They'll have AIX kernel data structures. They'll have like users, which contain the process and its related information, and then they'll have uthreads, which will contain thread and its all information. So different kernels can have different data structures. Now let us look at how do you implement these data structures. You can build any data structure that you want inside the Linux kernel. However, there are a few that are frequently used. First one is a linked list. So a linked list is where each node will contain the variable information and a pointer to the next node. We have different kinds of linked lists with single linked list, double linked list, circular linked list. However, the Linux kernel primarily employs intrusive linked list. It is a type of linked list in which each list node contains pointers to the next and the previous node. So you can consider it as a doubly linked list. And you can find the example implementation of a linked list in list.h file. Now, for any data structure to be efficient, we need to look at its complexities. In case of a linked list, the add operation and the remove operation are a constant time operation. However, searching through the linked list is a linear time operation. And the memory is going to be a constant time operation as well. Another commonly used data structure are queues. So queues are a data structure that work on a first in, first out basis. This is called FIFO. Data from a queue is being deleted in the order that it was being added, with the oldest data being removed first. Now, again, with queues, there are various implementations. However, Linux kernel specifically uses kFIFO implementation. The kFIFO object maintains two offsets inside the queue, an in offset and an out offset. The in offset is the location in the queue to which the next enqueue will occur, and the out offset is the location in the queue from which the next dequeue operation will occur. This is very similar to the regular queues that we use, which have a regular enqueue and dequeue operation, and all of the time and space complexities for a queue would be in constant time. Another common data structure used to improve performance is a map. A map is a collection of distinct keys, each with its own value. The Linux kernel specifically has an IDR map data structure, where IDR is used to translate user space UIDs such as POSIX timer IDs to the common corresponding data structures. There are various different ways to implement your map. You can either use a hash function to implement your map, similar to a hash map, in which case the complexities would be constant time, or you can use a hash tree, in which case the complexities would become of log n, logarithmic, and the memory complexity is going to be linear time. Lastly, let's look at trees. So there are several different implementation of trees. However, the one that we are going to focus on are red-black trees. So a red-black tree is a regular self-balancing binary tree. However, it is the fundamental binary tree that is built inside the Linux system. Red-black trees have either a red or a black color trait, and they maintain a semi-balanced situation by implementing several different rules. And you can find the implementation of red-black trees inside of rb-tree.h file. The complexity inside of a red-black tree is going to be logarithmic, and the memory complexity is going to be linear time. These were some of the most commonly used data structures inside the Linux kernel. All of these data structures can be combined and put inside of a rootkit inside the kernel. However, kernel-level rootkits can compromise system security by changing the critical kernel data structures to accomplish a range of harmful objectives. And developments are being made to create a unique rootkit detection approach that automatically detects rootkits that change both the control and non-control data structure, and then to remove them. This vulnerability is apparent in the memory. The kernel memory is unified and combines core kernel code with driver components of varying origin. Now, the kernel-level malicious software takes advantage of this lack of separation between the kernel and its module by changing the security-critical kernel data structures illegally. An access control data policy and enforcement mechanism is being developed to prevent kernel components with low trust from modifying security-critical data needed by the kernel to regulate its own execution. So there is a lot of research being done to minimize all of these vulnerabilities, and we shouldn't lose hope, and we should continue using these data structures. Next, let us look at what are the different kinds of data structures that we can use based on our use case. Let us start with linked lists again. So we should use linked lists if iterating over all of your data is your principal access technique, performance is not critical, or performing time-critical lookup operations is not important, storing a relatively small number of items or very large number of data, or if you want to communicate with Linux kernel code and make use of Linux lists. Use queues if your code adheres to the producer-consumer design pattern, and if you require a fixed size buffer. Use map if you want to map a UID with an object, or if you're dealing with descriptors distributed to user space. And lastly, use red-black trees when you want to store a huge amount of data and search for it very quickly.